Okay. Good afternoon, everyone. I'm Jianing Zhu, a PhD student from HKBU. Today, I'm going to host the 18th TrustML Young Scientist Seminar. Before that, allow me to briefly introduce Recon AIP to our vulnerable guest. The full name of Recon AIP is Recon Center for Advanced Intelligence Project. AIP was founded in 2016 as the research center for the next AIP project. AIP Center conducted Japan's leading AI research, which is handled by Professor Sugiyama. AIP aims to enhance AI fundamental technology and its real-world applications. AIP encourages the collaborations with various researchers and engineers in related fields. We would be grateful if you could visit us in the Nihonbashi office in Tokyo in near future. Today, we are very excited to have Mo-Xin Yang, who will give us the talk named Noisy Correspondence, a new paradigm for learning with noisy labels. Mo-Xin Yang is currently pursuing the PhD degree at the College of Computer Science, Sichuan University. His work focuses on multimodal learning and label noise learning, especially the combination of both. Hi, Mo-Xin. You can get started with your talk if you are ready.
All right. Thanks for the invitation of Jingfeng and the introduction of Jialing. I'm really honored to this talk. My name is Mo-Xin Yang. I'm from University, China. My topic is the new researches of our lab, namely noise correspondence, a new paradigm for learning with noise labels. And here is the outline of this talk. First, I will give an introduction of our newly proposed noise correspondence, which includes false negative correspondence, false positive correspondence, and the twin noise labels. In the real world, many applications highly rely on the data correspondence. There is the correspondence in the data pairs. For example, cross-modal retrieval needs the correspondence between the images and the captions. Feature grounding needs the correspondence with the image resonance and the queries. Similarly, in other applications, such as machine reading comprehension and the graph matching, also require the correspondence of pairs. However, in the real world, it's hard to collect high-quality label data. In fact, the data pairs are usually wrongly matched. Take the conceptual caption as an example. This is an automatically harvested dataset from the internet by selecting the images with the corresponding error text on the web. Although the authors have proposed to fail the noisy by several rules, it's reported to still have 3% to 20% noisy. Here we show some examples from the dataset. As shown, the images and the captions are wrongly matched, which is apparently undesigned for the downstream tasks. For example, the first images may be a lot of hay on the garden, while the corresponding caption is read between the lines, and your dream about the person will be clear. They are totally irrelevant. Formally, we call the natural noise pair in the data set as false positives. Besides, false negatives are the other common form of noise pair, especially in the contrastive learning paradigm. Specifically, as the figure shown, for a given anchor sample, its augmentation are positives, and the rest ones in the mini batch are regarded as negatives. However, there are some semantic positive pairs while are wrongly treated as negatives. As the figure shown, the dog in a red box is actually with the same category of the positive dogs, while it's wrongly treated as negatives. We call these pairs as false negative pairs. The false negative pairs will be harmful for the representation learning. Meanwhile, false positive and the false negative will be introduced in the metric learning when the annotations are noisy. Since pairs are constructed according to the annotation, we call the noisy annotation and the accompanying noisy correspondence as twin noise labels. In our recent studies, we first formally define the above noises as noisy correspondence and propose a series of solutions. Compared to the traditional noisy labels, noisy correspondence refers to the alignment errors in the data pairs rather than the errors of category label annotation in a single sample. In general, noisy correspondence could be regarded as a new paradigm for noise labels, which extends the application scenarios of noise labels. In the rest, I will introduce 3 forms of noise correspondence in the solutions in detail. To begin with, we first introduce the partially view-aligned representation learning task, where we solve the false negative correspondence issue. The existing multi-view learning methods heavily depend on 2 assumptions, namely the completeness of data and the consistency between views. However, these 2 assumptions are easily violated, which lead to the so-called partially data missing problem and the partially view aligned problem. Partially data missing refers to the missing data in some views. Partially view aligned means that only a portion of cross-view correspondence are known. The rest ones are unknown. For example, 3 cameras are corresponding to 3 views, while the second one has blocked down, which leads to the data missing problem. In the second panel, different cameras should have shot the same humans. However, it's violated due to the spatial temporal discrepancy, which leads to the view unaligned problem. In our research, we focus on the partially view aligned problem. Instead of achieving the instance level alignment, our basic idea is to achieve the category level alignment, namely establish the correspondence between 2 cross-view samples in the same category. Intuitively, on the one hand, for each instance, it has a probability of 1 in k to be realigned correctly in a category level manner, instead of 1 in n in an instance level manner, where k is the class number and the n is the instance number. On the other hand, the category level alignment is enough to the classification tasks, which are verified in the experiments. Again, we want to deal with the partially view aligned data and achieve category level alignment. To this end, we reformulated it as a category level identification task, namely identify whether the given 2 samples belong to the same category. One direct idea is regarding the cross-view samples of the same category as positives, while treating the cross-view samples of different categories as negative pairs, and further use constructive learning to solve this task. However, these solutions relies on the label information while our method focuses on solving partially view-aligned problem under the enable setting. Therefore, under the enable setting, we constructed the positive pairs using the available aligned data and the negative pairs using random sampling. Apparently, such a solution would introduce false negative pairs, namely symbols of the same category, which should have been regarded as positives, while wrongly treated as negatives, to eliminate or even eliminate the influence of the false negative pairs caused by random sampling. Our model is with a normal noise-robust contrastive loss. The proposed method consists of pair construction and the noise-robust optimization. Specifically, in the pair construction module, we pass the constructed pairs into two encoders to get the view-specific representations. Note that the negative pairs will have a probability of 1 in k to be false negatives, where k is the class number. As the result shown in figure C in D, if we use the linear contrastive loss to optimize the network, it will fit the false negative pairs and only increase their distance. To prevent the wrongly fitting caused by the linear contrastive loss, we propose the noise-robust contrastive loss, which could be one of the first attempts to make contrastive learning robust to false negatives. Figure A and B are the loss spaces of the two losses with respect to the distance of negative pairs. From these surfaces, one could know that our loss was the reverse optimization and the slow optimization properties. When the negative pairs fall into the areas of 0 to m third, the direction of the gradient will be reversed so that the distance of false negative pairs would decrease. When the negative pairs fall into the area of m third to m, the gradient will be reduced so that the only increasing distance of false negative pairs will be slowed down. The two properties enable the constructive learning robust to false negatives. In the experiment, we visualize the pair distribution and the realignment results from the noise minister dataset. In the top panel, one could see that the distance of FMP underlie robust, namely false negative pairs without robust loss, would be correctly minimized compared to the ones with linear loss. Meanwhile, the distance distribution of false negative pairs without robust loss resemble the ones of PP, namely positive pairs. The results show that our robust loss could correctly treat the false negative pairs as positive pairs, which would prevent the model from wrongly fitting false negative pairs. We also visualize the re-established correspondence on the noise minister dataset. In brief, we handle the partially view-aligned problem by endowing constructive learning with the robustness to false negative pairs. This work inspires us to realize the importance of noise correspondence and pull us to the study of noise correspondence in different forms and tasks. After realizing the importance of handling false negatives, we formally take noise correspondence and enrich it with false positive correspondence. Apparently, noise correspondence will degrade the performance of various tasks, including cross-modal matching. As the figure shows, the wrongly matched pairs are the false positives, which guides cross-modal matching with the wrong direction. In fact, it's expected to minimize the similarity of such wrongly matched pairs, rather than enlarging their similarities. To the best of our knowledge, there are no works so far to solve this question in multimodal learning. To solve this false positive correspondence issue, we propose a normal method called noise correspondence rectifier, NCR. In brief, for the noise data, NCR first divides the data into noisy and unnoisy subsets, and then rectify the correspondence with the model predictions. Finally, NCR achieves robust matching by recasting the correspondence into soft margins, as shown in the right figure. The false positives are correctly revised as negative pairs. After performing NCR on the noise data, we eliminate the undesired impact from noise pair and even completely transform the false positives into true negatives. Some early works have shown that deep neural networks first learn the simple and the general patterns of the real data before fitting the noisy, which is called the memorization effect of networks. As shown in the figure, with the noise data, it achieves the best performance in the initial several epochs and decreased with further training. Such a result verifies the memorization effect of deep neural networks. Motivated by this, NCR first divides the data into a relatively clean and relatively noisy subset based on the loss difference. In detail, we first warm up two networks with vanilla triplet loss individually. Then we adopt the Gaussian mixture model, GMM, to fit the loss distribution and compute the post probability of the component with a small mean value as the clean confidence of each pair. As shown in the figure, the Gaussian mixture model fits the noise data pretty well and can only fix the data into noisy and clean subsets. With the divided subsets, we can rectify the correspondence via the model predictions. Since the cross-modal matching has no prediction method, but a similarity measurement, we design a prediction function by considering the margin to be the average similarity of the top positive pairs in a mini batch. Then we combine the clean confidence and the model prediction to refine the correspondence. As we can see in the experiment results, most noise pairs are refined to 0, which denotes totally unmatched. Finally, with the refined correspondence, we perform the robust matching by recasting them into soft margins. As shown in the right figure, we assign adaptive margins to the pairs in terms of the refined correspondence. In other words, we assign a small margin to the probably noisy pair, while a large margin to the clean ones, and achieves robust cross-modal matching. Combined with all above, we give a summary of the proposed method here. First, NCR divides the data into two relatively partitions based on their loss difference. Then we rectify the correspondence by an adaptive prediction functions. Finally, we train the machine model with a normal triplet loss by recasting the rectified correspondence as the software margin. We perform experiment on the benchmark dataset EMS COCO and the Flickr. One could observe that NCR remarkably outperform all the baselines by a large margin on the noise data. Note that in the noise-free setting, NCR still achieve competitive results. We also conduct experiments on the noise data from the wild, that is, on the conceptual caption dataset. As shown, NCR remarkably outperform all the baselines by a large margin on this real-world noise dataset, showing the effectiveness against to the real noise. Here, we show some noise pairs found by our method on this dataset. In addition, we also compare NCR with the large pre-trained model Quadruplet, which use millions of image test pairs for training and achieves competitive results in many downstream tasks. We can see that the importance of Quadruplet, the performance of Quadruplet decreased when fine-tuning on the noise data. In contrast, NCR achieves permitting matching performance. Such results shows the importance of methods for handling noise correspondence. Moreover, it also shows that having large amounts of noisy image test pairs isn't enough, and the performance of the downstream tasks can be further boosted by handling the noise correspondence in the method. Moreover, NCR is the general framework to enable machine model robust to noise correspondence. Here, we extend the scan into NCR framework and report the performance on various noise ratios. The results show that the generalization of our method to different models and the different noise ratios. In this work, we formally reveal a new paradigm for noise labels, that is, noise correspondence, which is different from the existing noise label learning. NCR is the first work to solve noise correspondence for cross-modal matching. To this end, we propose an adaptive prediction function and a soft margin-based triplet loss. After reviewing the false negative and the false positive correspondence, we further explore a special twin noise label issue, where the noise correspondence are caused by noise labels. We studied the twin noise label issue in the visible infrared person re-identification task. And I will first introduce this task. Person re-identification is the task of searching different shows of a specified person from the database. Although the traditional person re-ID methods have made progress, this works mainly focus on searching RGB images captured by the visible cameras, which may fail to achieve encouraging results under poor light environment, such as the night. Today, many monitors can automatically switch from the visible into the infrared mode. under the darkening elements. Therefore, it's highly expected to develop person searching between the visible in the infrared modalities. To this end, the visible infrared reality task, which aims to find the corresponding identities across two modalities, is proposed. The existing visible infrared reality methods usually use the identity annotation to calculate the cross-entropy loss. In the meanwhile, establish the cross-modal correspondence by calculating the triplet loss, where the photos of the same person from different modalities will be regarded as positives. And the photos of different persons will be treated as negative pairs. After that, the identity-aware discrimination will be enlarged, and the cross-modal discrepancy will be eliminated. The current visible infrared methods heavily require the faultless manual labeling, so that the identity annotation and then the accompanying cross-modal pair or triplets are clean. In practice, however, it's daunting and even impossible to precisely annotate all samples due to the poor recognizability. Especially, the color information is lost in the infrared modality. Therefore, the twin noise labels will be introduced. Specifically, twin noise label refers to the noise identity annotation and the accompanying noise correspondence. Here, noise correspondence consists of false positives and false negatives, where the false positives refers to samples of different identities, while only treated as positives. And the false negatives refers to samples of the same identities, while only treated as negatives. The above twin noise labels will heavily degrade the performance of the existing methods. To solve the twin noise label issue, we propose duly robust training, namely DART. DART first models the clean confidence of an annotation by resorting to the memorization effect of deep neural networks. Based on the confidence, DART divides the noise pair into four subsets and rectify the correspondence. Finally, DART employs a normal duly robust loss, which consists of a soft identification loss and an adaptive cross-overlay loss to achieve robustness on the noise annotation and the noise correspondence. In detail, the confidence modeling relies on the memorization effect of neural networks. First, to fit the sample of clean annotations, we train two individual networks using the linear cross-entropy loss. Then, to compute the annotation confidence, we fit the sample loss distribution of all training data by modeling a two-component Gaussian mixture model. Due to the memory effect, after one up, compared to samples of long annotations, the loss of clean samples tend to be relatively small. Therefore, we could take the Gaussian component with a small mean value as the distribution of clean samples loss, while the high mean value ones as the distribution of noise samples loss. Then we use the posterior probabilities over the small mean value components as the correctly annotated confidence. After that, based on the confidence, that divides the pairs into 4 groups and rectify the correspondence. Specifically, if the confidence of 2 samples are greater than a specific threshold, they will be treated as a clean pair. Otherwise, they will be regarded as noisy pair. Apparently, the clean set would contain 2 positives and 2 negatives, while the noisy set would contain false positives and false negatives. Then we rectify the correspondence of these pairs. With the above operations, we could finally get 4 combinations of triplets with their rectified correspondence. They are true positive and true negative, true positive and false negative, false positive and true negative, false positive and false negative. Finally, based on the confidence in the pair divisions, we design a 3 robust loss, which consists of source identification and the adaptive quadruplet loss. The source identification loss aims to pairinize the wrongly annotated sample using the modeling confidence. The adaptive quadruplet loss aims to achieve robustness on the noise correspondence, which consists of a special triplet loss in the adaptive quadruplet loss term. This is the overall loss. The quadruplet loss could adaptively switch into different forms in terms of the types of input pairs. For example, for the combination of false positive and the false negative, this loss would change its optimizator direction to enlarge the distance of false positives and reduce the distance of false negatives. To verify the effectiveness and the robustness of our method, we conduct experiments on the visible infrared datasets with noise ratios varied from 0% to 20% to 50%. And compare with 5 SOTA baselines, the result shows that our method achieves competitive or better performance compared to the baselines under different noise ratios. On the RecDB dataset, the proposed method also achieves better performance. In terms of twin noise level, one director in the ideal solution is collecting all the long annotations, which could meanwhile avoid the noise correspondence. However, the reality dataset always consists of thousands of identities, which cause trouble for the annotation correction. The halfway correction on annotation could not fully avoid the noise annotation and the accompanying noise correspondence. To verify our argument, we use the SOTA baseline on learning with noise labels, namely divide mix. We designed 2 variants of divide mix to process the noise data. After that, the SOTA visible infrared methods, namely ADP, is performed on this data. As the results shown in the top 2 tables, divide mix cannot achieve considerable divided or revised SSA on reality dataset, so that the performance would also decrease, as shown in the bottom table. Therefore, in the reality dataset, it's hard to precisely correct the annotation so that the twin noise level issue is avoided. In other words, it's important to handle the twin noise level issue. Furthermore, we visualize the sample identification loss distribution of all twin samples before and after warm-up. Compare figure C with D. One could observe that training with our soft identification loss, the model not only fits the clean samples well, but also avoid only fitting the noisy. Meanwhile, we visualize the pairwise distance distribution of true positive and false positive pairs, true negative and false negative pairs. As shown in figure B in D, our data could prevent the model from only fitting noisy pair. For example, in the figure B, false positive pairs are correctly regarded as negative pairs, and their distance are decreased. As that actually is a robust framework, we also extend that on one of the classical visible inference methods, namely HEW. Here, we show the results of HEW and the HEW with our data on two data sets with the varying noise ratios. As you can see, HEWs performs worse with the increasing noise ratios, while HEW with our data usually keeps stabilities. In a word, this work reveals the twin noise label issue, which includes noise annotation and the accompanying false positive and false negative pairs. The twin noise label issue first further enriches the noise correspondence topic. Okay, in the last, I would to summarize this talk. In this talk, I introduced the new researches of our lab, namely noise correspondence, which refers to the mismatched pairs. Compared to the traditional noise labels, noise correspondence refers to the alignment errors in the paired data, rather than the errors of category annotation in a single sample. Therefore, noise correspondence could be regarded as a new paradigm for learning with noise labels. Until now, we have enriched the definition of noise correspondence by taking different forms in different tasks into consideration. There is the false negative issue in contrastive learning, false positive issue in cross-modal matching, twin noise label issue in person re-identification. Besides our studies, there are many tasks and the scenarios needing data pairs, such as the machine translation, visual grounding, which would also encounter noise correspondence issue. Therefore, I believe noise correspondence will be an important and valuable topic in the future researches. Okay, that's all for my talk. Thanks for listening.
Okay, thanks, Moshin's great talk for the today's seminar. And is there any question from our audience for today's talk? Maybe I have several questions for your great talk. The first one, could you go back to the conclusion page in your slide? Okay, thank you. It seems that the noisy correspondence is a new paradigm that's different from the noisy label. My first question is that is there any method to measure the degree of mismatching in the noisy correspondence? I mean, can we quantitatively to measure the mismatching degree of the correspondence?
Yeah. This is a good question. As I know, there are no methods so far to measure the noisy ratio in the noise correspondence. Our method our method mainly mainly focus on selecting the clean pairs and the noise pairs and further handling the noise pair.
So we can say the image is not correspond to the text, and the another image is correspond to the right text. Is that right?
Yes.
Oh.
Yes.
Okay.
Indeed, there are many application scenarios, such as the images and the captions are unmatched. It's one of the scenarios, and then the other scenarios could be the question and then the answer are unmatched in the machine translation, and the image reference and the queries are unmatched in the visual grounding task.
Yes.
And also in the video analyze task, the visual and the audio are also unmatched. There are also the application scenarios of noise correspondence.
Okay, thanks. And my second question is that if you have a chance to further revise your method like Dart, is there any opportunity to further improve the performance of your work like Dart?
Do you mean that are there any further improvement to our data?
Yes. From any perspective.
Yeah. Okay, actually, we are now doing improvement on that. The improvement is mainly on the handling on the noise triplets.
Okay.
As you can see now, we handle the noise triplets by different forms of the special triplet loss, and we are now handling them by a more specific form.
Okay, I see. Thanks. Thanks for your answer. Let me check. Is there any question from the from our audience or the chat box?
Okay, thank you.
Okay, it seems there is no other questions for today's talk. Maybe it's the end of today's talk. And thanks Moxin again for joining the TrustML Young Scientist Seminar. And thanks for your great talk.
Okay, thanks for Jialing. And you also have any questions, please feel free to send me an email to this address. Thank you.
Okay, sure.